This video discusses how to differentiate tangent x. Please note that there are two very popular methods to differentiate tangent x. One is using the first principles, the other one is using the quotient rule along with the results of sin x and cosine x differentiations. In this video, I'm going to talk about the proof of tangent x differentiation using the first principles. First of all, let me write down the result if you differentiate tangent x. Let's say you need to differentiate tangent x with respect to x. This will be equal to secant squared x. We will see how to prove this result using the first principles. The use of the first principles is not the most efficient way to do this unless the professor wants you to do it using the first principles. Here is the proof using the first principles. Of course, as always, for the first principles, we need to define a function f of x. We know that the function f of x is going to be the given function to be differentiated. Therefore, we need to define f of x as tangent x. After that, if you are going to use the right-hand differentiability, we are going to need f of x plus delta x as well, which will be equal to tangent x plus delta x. Now we have everything necessary to write down the right-hand differentiability for the first principles. If you would like to go for the left-hand differentiability, please make sure to write down f of x minus delta x. No matter whether you are going to use the left-hand differentiability or the right-hand differentiability, you must get exactly the same answer. Since I would like to go for the right-hand differentiability, let me first go ahead and write down the generic equation, which is d plus at x equals limit as delta x approaches to 0. What do you have on the numerator? We have f of x plus delta x minus f of x. In the denominator, we have a delta x. Now let's go ahead and write down these functions for our case. D plus at x equals x. This is equal to limit as delta x approaches to 0. On the numerator, f of x plus delta x. For our case, it is tangent x plus delta x. That minus f of x is tangent x. In the denominator, we have a delta x. For most of the textbook proofs of tangent differentiation using the first principles, they convert both of these tangent functions into sine and cosine functions, and then they do some further simplifications. However, it is not required to be done as that if you use an identity from trig. The identity that I'm going to use is tangent a minus b. You know, tangent a minus b is equal to tangent a minus tangent b. All of that's divided by 1 plus tangent a times tangent b. If I rearrange the terms of that identity a little bit by multiplying both sides by the denominator 1 plus tangent a times tangent b, I can get rid of that denominator on the right-hand side and it will appear on the left-hand side with multiplication of tangent a minus b term. Then it will become 1 plus tangent a times tangent b times tangent a minus b is equal to tangent a minus tangent b. Now I'm going to use that result for the numerator of the right-hand differentiability right here, with a equals x plus delta x and b equals x. You can see that the highlighted numerator of that right-hand differentiability is similar to the right-hand side of this identity. Therefore, as soon as I put a equals x plus delta x and b equals x, I can apply this left-hand side of this identity for that numerator on the right-hand differentiability. The right-hand differentiability is now going to be equal to limit as delta x approaches to 0. On the numerator, we have tangent x plus delta x minus tangent x. We know x plus delta x is going to be considered as a and x is going to be considered as b. Then the first term is, let me open parenthesis, 1 plus tangent a times tangent b. Tangent x plus delta x times tangent x, close parenthesis. And the second term right here is tangent a minus b. Since a is equal to x plus delta x, b is equal to x, a minus b, x plus delta x minus x is equal to delta x. Therefore, this has to be multiplied by tangent delta x. In the denominator, right here, we have another delta x term divided by delta x. Now, how would you simplify this? We can simplify this easily using a trig limit that we have seen in the past. The trig limit that we have seen involving tangent is right here. Limit as u approaches to 0, tangent u divided by u is equal to 1. If you look at this part, you can see it's going to be a tangent delta x over delta x, and that delta x is approaching to 0. For this theorem, I need these three places to have exact same figure, and that figure should go to 0. Of course, I have exact same figure in these three places, and that figure goes to 0. Therefore, this part of the limit problem should be equal to 1. Then I can do the direct substitution of delta x equals 0 for this remaining component of that function. When I put delta x equals 0, this part, which is the only remaining part of that limit problem, is going to be equal to 1 plus. Since delta x is 0, this first tangent x plus delta x term becomes tangent x. The next term is also a tangent x. When those two are multiplied with each other, we get tangent squared x. Now, what is this? From the second of the three Pythagorean identities from trig, we know that this is equal to secant squared x. We completed the derivative of tangent x with respect to x. This is equal to secant squared x. This is also one of the very important results of differentiation. Thank you so much.